Hello, my name is Maciej Hałaszkiewicz. I am a part of Team E along with Benjamin Iglesias. And our project this semester has been on thorium-based nuclear power with a focus on the advantages and disadvantages. I'll be doing my oral presentation today on the history and the disadvantages of thorium. The history will be covering John Jacob Berzelius, Marie Curie, military applications, Hector A. d'Auvergne, and the Shippingport Atomic Power Station. In 1828, the element thorium was discovered by Jöns Jacob Berzelius in Norway. He named it after the Norse god of thunder, Thor. This element had little industrial application, so it was pretty much forgotten until 1898, when Marie Curie discovered that thorium had radioactive properties. Until about 1945, the world was mainly concerned with the nuclear arms race and creating nuclear weapons. After that, the United States began theorizing the use of nuclear power as a source of sustainable energy for aircraft and ships. Two materials were being considered at the time, thorium and uranium. The government decided to merge their nuclear program with the civil nuclear programs in order to produce nuclear power plants more effectively. Because of the desire to maintain a continual effort to obtain material for nuclear weapons, the US government decided to use uranium instead of thorium. In 1965, the d'Auvergne Brothers Industries began developing a thorium reactor under the guidance of their founder, Hector A. d'Auvergne. In 1987, the company closed down due to lack of funding and support. With the help of Ford Laboratories and the University of California, Berkeley, DBI reopened in 1991. Since 2009, DBI has been accumulating funds and support in order to begin production of their first reactor plant. So Shippingport Atomic Power Station, which is located in Pennsylvania, was the first commercial plant operating in the world. And in 1977, the plant decided to experiment with thorium-232 fuel cycle. They successfully generated 2,100 gigawatt hours of electricity for over 29,000 power hours. Thorium fuel achieved maximum burnup of 60,000 megawatt day tons without fuel failure. Even today's reactors have not achieved such an outstanding performance. Although the thorium was used to manufacture uranium-233 in a separate location, it proved that with the proper research and support, thorium had the potential to be a more efficient and reliable fuel. The operation lasted until 1982 using a light water reactor. Since then, many attempts have been made to use thorium in existing plants, but the majority of them have been unsuccessful. The future of thorium-based nuclear power looks bright. In 2002, India was approved to begin production on their advanced heavy water thorium reactor, and in 2011, China has begun their design and production of the liquid fluoride thorium reactor. Russia, Japan, France, and the United States are all also working on new designs for reactors or reopening their old research in order to find ways to implement thorium into their power plants. Compared to uranium, thorium actually has very few disadvantages. We'll be going over the cost, fissile material, long interval breeding, the environmental impact, health risks, and proliferation. One of the main concerns with the use of thorium as a nuclear fuel is the costs that are associated with implementing a new technology into the infrastructure of an existing society. Introducing thorium into existing nuclear reactor types would lead to excessive cost issues associated with installation and maintenance of thorium reprocessing and fabrication facilities. By using this process, the demand of reprocessing produced fissile material would be a great cost over time, which would make it more sensible to begin the installation of new reactor designs, specifically the advanced heavy water reactors and the liquid fluoride thorium reactors. To begin building and operating thorium reactors in the United States today would cost a good sum of money. A 1 gigawatt thorium plant would cost approximately $250 million in construction, and the operating cost would be about $5 million, while the fuel cost would run approximately $1 annually. This is much lower than a uranium plant, and over 60 years would save a lot of money, but the initial cost is what would be a concern for the implementation of this into our energy system. Thorium alone is not able to efficiently begin fission because it's not a fissile material. This could pose a problem. Because thorium is fertile, it must have neutron absorption caused by the introduction of other fissile products in order to begin the chain reaction for the nuclear power cycle to begin its process. This means it'll be necessary to add another element into the thorium-based reactors in order to operate them. Two such elements could be used to initiate the thorium fuel, the uranium and plutonium. Although there would not be much of the material being used to make the thorium reactors begin operations, the removal of uranium and plutonium from nuclear power plants is not possible at this time. One of the main problems with thorium-based nuclear power is long-interval breeding. Fissile material at the moment is a requirement in thorium-based reactors for starting up the plant. To breed thorium-232 to uranium-233, a driver fuel is needed, plutonium or uranium. Otherwise, there are insufficient neutrons generated to keep the process going. Today's nuclear reactors undergo a simple and fast decay, allowing for efficient attenuation of reactors. In the case of thorium-driven nuclear reactors, long-interval breeding occurs. Long-interval breeding takes a substantial amount of time for the thorium decay product, protactinium, to breed into a fissile uranium. It's approximately 27 days. Protactinium converts into non-fissile isotopes. This reduces the efficiency of the reactor and the neutron population by adding 2 more neutron absorptions before the fissile product is created. It is a very effective absorber of neutrons, and because of this, it would delay the attenuation of the reactor, making it less efficient. In order to correct this problem, a process to separate protactinium from the active zone would need to be created so that the thorium could decay into uranium-233. So with regards to the civilian aspect of thorium-based nuclear power, there are a few environmental impacts and some health risks involved. The spent fuel from thorium reactors, if not reprocessed, has a half-life of 14 billion years, allowing for the buildup of decay products over time, making the spent fuel extremely radiotoxic. Another issue with thorium-232 and its decay product thorium-238 is that these elements provide a higher dose of radiation to organs if inhaled than the dose provided by uranium. If not properly handled, the same unit dose of thorium is near 200 times larger than the same amount of uranium. One of the byproducts of uranium-233 is uranium-232, which is highly radioactive. So more stringent precautions will need to be taken in order to ensure the safety of workers. As long as the nuclear plant associated with thorium are kept under stringent rules and regulations, there should be no problem with the risks associated with thorium decay products. So thorium is found pretty much everywhere in the world in very small amounts. However, in large doses, thorium causes many other health risks. It has the ability to change genetic material, and as a result, when thorium dust is breathed in, it can cause lung damage and increased risk of lung and pancreatic cancer. When large amounts of exposure take place at extraction facilities, the possibilities of metal poisoning is also a great concern. And thorium is radioactive, and so it has been known to have been stored in bone tissue, causing bone cancer. There's even some evidence that shows that thorium can be absorbed through the skin. Although not the primary form of entry, skin absorption could cause higher risk of long-term radiation exposure. All of these issues are much harder to detect because of the lack of medical equipment in most hospitals that have the ability to detect thorium exposure. This makes the possibility of early detection more difficult. Although not very practical, the possibility of proliferation does exist with thorium-based nuclear power. You would have to extract about 8 kilograms of uranium-233, which would take around a year with today's technology. The problem with that is it would cost a lot of money, and you would have to separate it from uranium-232 and worry about thallium-208, which is a gamma emitter that would irradiate the housing and electronics of the weapon, causing it to be inoperable. So even though there is proliferation risk, when using thorium to fuel a reactor, it seems impractical to put the amount of effort and money into such a project to create a nuclear weapon that would harm even the user of the device. The difficulty associated with separating uranium-233 by the most advanced countries in the world is enough to assure the public that terrorist groups or other countries who wish to get their hands on nuclear weapons will not be able to utilize the fission product as a bomb. Learning about thorium-based nuclear power this semester has been an incredible joy, and I hope that they actually try to utilize this as a replacement for uranium-powered reactors. Thank you for listening to my presentation.